everyone, today we are going to see how crystal field theories explain the color of coordination compounds. Any substance appears colored, it is because that substance absorbs the visible region of the electromagnetic spectrum, that is from the sunlight. The visible region has a frequency, has the wavelength of approximately 400 to 700 nanometer. The visible region or the visible light is made up of VIBGYO, that we all know. VIBGYO. These are the colors that are broadly arranged into these colors. And if any substance has capacity to absorb the radiation in this wavelength, that substance will have the complementary color of the color that is absorbed. For example, if a substance absorbs yellow from the visible region, that will appear as violet. So what happens is that a substance is absorbing certain wavelength of energy, and that is retained in the substance, and all the other colors are getting ejected from it, getting reflected from it. And so this substance will appear the color that is complementary to the absorbed color. So while coming to the coordination compounds, what is happening is that this difference between the T and E levels is in this region between 400 to 700 nanometers. So in complexes, an electron absorbs energy in this region. An electron in the lower level absorbs the energy corresponding to the visible region and gets excited to the higher D levels. So the crystal field splitting energy for most of the complexes are in the range of visible region of the electromagnetic spectrum. So that's why most of the complexes are colored and highly colored. So this is how the crystal field theory is explaining the color of coordination complexes. For example, take this complex. The wavelength of light absorbed is in the region around this 535, and it's corresponding to the yellow. And the complex, that means this complex will absorb yellow radiation. So all the other radiations other than yellow will be reflected back, and the complex will appear violet, that is complementary to the yellow color. So this is an example of different complexes and their color. This complex, this cobalt complex, is absorbing radiation of the wavelength 500, and it appears red because the color corresponding to 500 nanometer is blue green, and the color corresponding to this is red. So similarly, the color of complex of hexamine cobalt is yellow orange because it absorbs blue visible radiation in the frequency of 475. Similarly, when the complex's ligand is Cn minus ion, that happens, it absorbs ultraviolet radiation of wavelength 310, and it appears pale yellow in color. So for copper aqua complex, it absorbs wavelength in the region of 600 nanometer and appears blue because the radiation, color of radiations corresponding to 600 nanometer is red. And for titanium aqua complex, the absorbed radiation is in the 498 nanometer, similar to that of 500 nanometer, and the complex is violet since the radiation absorbs has a color of blue-green. So this is how the crystal field theory explains the color of complex. The reason is DD electron transfer. So the main reason for color is DD electron transfer. This is happening because this difference in D orbitals is in the range of visible region of the electromagnetic spectrum from the solar light. This can be understood from these examples. This complex, this titanium hexaqua complex, on heating renders it colorless. What happens is that when heated, this water molecules get released from this complex, and this complex will no longer be a coordination complex. It will become a titanium normal compound. So what happens when there are no ligands? There is no crystal field splitting. So if no ligands are present, when ligands are coming, only the crystal field splitting is happening. If there are no ligands, no crystal field splitting. So there is no separation of DD orbitals into two. So the energy corresponding to visible region is not absorbed by the molecule. So the complex is colorless. Similarly, anhydrous copper sulfate is white. The normal copper compound is white, but copper sulfate 5H2O is blue in color. Because when here the H2O molecules are acting as the ligands, thereby this becomes a coordination complex, and there is DD splitting that is corresponding to the visible region. So the energy corresponding to the visible light is absorbed. So the complex will appear in complementary color of that radiation that has been absorbed. So to understand this, an experiment is done. For this, a complex having this structure, that is nickel hexamine hexaqua complex, which is green in color. This is the complex. It is treated with another ligand, that is a strong ligand, ethylene 1,3-diamine. So when they are treated, this ethylene diamine is progressively added. And when one ethylene diamine ligand is added, the color of the complex changes to pale blue. And to that complex, when ethylene diamine, one equivalent of ethylene diamine is added, the complex changes to this ethylene diamine twice, and the color changes to blue or purple. And to that complex, when an equivalent of ethylene diamine is added, this complex is obtained. That's nickel ethylene diamine thrice, and it is violet in color. So when stronger ligands are added, ethylene diamine is a stronger ligand. When stronger ligands are added, what happens? When ligand is strong, means high crystal field splitting. That means the energy gap becomes wider. So what happens? The absorbed radiation will be of higher frequency or lower wavelength. So the complex will have colors in this order, from blue to indigo to violet, because violet is the higher energy or the lesser wavelength region in the visible spectrum. So this is also the reason for appearance of bright colors in precious stone. For example, in emerald, a precious stone, what is the color of emerald? It's green in color. It's a bright green in color. So the structure of emerald is like this. The mineral beryl, that is B3Al2Si6O18, is the structure in which the gaps, the octahedral sites of the minerals are occupied by Cr3+ ions. So what happens? There is DD splitting is happening, and the absorption bands shift to a longer wavelength. Longer wavelength means towards the red. So red will be absorbed more. So the complex or the emerald will appear complementary to red. So the in the opposite spectrum of the VIBGYOR, that is in the blue-green region. So, therefore, by the absorption of yellow-red radiation, emerald transmit the light in the green region. So, this emerald will appear highly colored. And for the case of ruby, what's the color of ruby? Ruby is bright red. So, structure of ruby is like this: aluminum oxide containing about 1% of Cr3 plus ions. And normally, so in the structure, crystal structure, the positions, some of the positions of Al3 plus ion is occupied by Cr3 plus ions. So what happens? The DD transmission, the crystal field splitting is happening, DD electronic transmission is happening in the range of visible region, and we can see the radiation absorbed will be in the region of blue-green. So the complex will appear ruby. So the reason for appearance of bright colors in precious stones like emerald and ruby can be explained in the basis of crystal field theory. This is what we have seen in this class. I hope everything is clear to you. If you have any doubts, please ask me in the comment section. Thank you for watching. Happy learning.